Welcome to this clinical explainer. Today, we're breaking down the QT interval on an ECG. It's literally just a tiny space on the grid, but getting this one measurement right, it can absolutely mean the difference between life and death for your patient. Let's dive in. In this quick teaching module, we'll cover defining the QT interval, mastering the measurement, calculating the corrected QT, and then we'll look at both prolonged and short QT scenarios in the real world.
All right, Section 1, defining the QT interval.
So what is it exactly? Well, the QT interval is simply the time from the start of the Q wave to the very end of the T wave. Physiologically speaking, this represents the entire duration of ventricular depolarization and repolarization. Basically, it's the full period of ventricular systole wrapped up into one measurement.
Looking at the grid here, you can see the QT interval highlighted in green. It's a precise window. And miscalculating it? Well, that can lead to missing deadly arrhythmias like Torsades de Pointes. That's exactly why we've got to get this right. Moving right along to Section 2, mastering QT measurement. Okay, this is where the rubber meets the road, the maximum slope intercept method. It's a brilliant trick for finding the true end of the T wave. You just draw a line down the maximum slope of the T wave, that's the red line here, until it intersects with the blue isoelectric line. Bam! That intersection point, that is your exact endpoint.
Now, when you're actually at the bedside, always measure several beats. You'll want to use either lead 2 or V5 to V6. Just go with whichever lead gives you the longest measurement. Oh, and here's a crucial rule of thumb. Absolutely include large U waves that fuse with the T wave, but totally ignore the smaller, distinct ones that stand apart.
Section 3. Calculating corrected QT, or QTC. Here's the golden rule of the QT interval. It's got an inverse relationship with heart rate. So it shrinks when the heart beats faster and stretches out when it beats slower. Because of this moving target, we have to mathematically estimate what the QT would be at a standard resting rate of 60 beats per minute. That gives us the true picture of the patient's risk.
To do this, we use a few different formulas like Bazett, Fridericia, Framingham, and Hodges. Now, I know we all use medical calculator apps to do this math instantly, but as a clinician, it's absolutely vital you know which formula to actually trust.
For instance, the Bazett formula from 1920 is definitely the most common because it's just so simple. But actually, it overcorrects at high heart rates and undercorrects at low ones. So if your patient's heart rate falls outside that standard 60 to 100 beats per minute sweet spot, you really need to switch over to Fridericia or Framingham for accuracy.
Section 4. Prolonged QT clinical scenarios.
Let's look at a real tracing. This patient has a dangerously low potassium level of 1.9. Notice how hypocalcaemia causes an apparent QTC prolongation right up to 500 milliseconds. This happens because the T wave is literally fusing with those prominent U waves. You can see it really clearly right there in the precordial leads.
Next up, myocardial ischemia. This typically produces a modest bump in the QTC, usually landing somewhere in the 450 to 500 millisecond range. This is a massive clue. It can actually help you distinguish a deadly hyperacute MI from a completely benign early repolarization, which usually just presents with a normal QTC.
Now check out this dramatic scenario. This is a sudden rise in intracranial pressure from a subarachnoid hemorrhage. Notice those characteristic cerebral T waves. You've got these widespread, super deep T wave inversions paired with a massively prolonged QT of 630 milliseconds. It is an unmistakable, critical pattern.
All right, our final section, number 5, short QT clinical scenarios.
You know, while a prolonged QT screams Torsades de Pointes, an abnormally short QT is just as terrifying. It warns us of a massively heightened risk for sudden cardiac death through paroxysmal atrial and ventricular fibrillation. Both of these extremes need your immediate attention.
Take a really close look at this tracing. See how hypercalcaemia physically shortens the ST segment? It drastically compresses the QTC down to just 260 milliseconds in this patient. That is just remarkably short.
Finally, if your patient is on digoxin, you've got to look for this classic visual pattern. You'll see a relative shortening of the QT interval coupled with that downward sloping reverse tick as T depression. It kind of looks like a backwards check mark, especially visible in those lateral leads.
By mastering the rules of measurement and rate correction, you're transforming just a simple space on a grid into this incredibly powerful diagnostic lens. You'll be ready to catch these hidden pathologies in your very next patient. So, I'll leave you with this thought. The next time you see a shortened or prolonged QT, will you know which hidden pathology is hiding behind the waves?